Hello, folks. Welcome to a deep dive. We'll get going here in a few minutes. If you're watching this recorded, make sure and check the description below for time codes. And yeah, so check that out. Check out the time codes. Thanks in advance to David for putting those in there. And somebody wants to help out with those. I think David's on vacation a few weeks, so we can talk about that later. Yeah, so I'll say hellos and we'll get going here in just a bit. Folks are passing the link around. Thank you, folks. Hi, G3 Holiday. Hi, Theronius PX. Something like that. Hi, Yanni. Hi, Dexter. Hi, Bruce S. Hi, MD Roberts. Good morning, Unexpected Maker. I think I've got all the chats up. Good evening, Christian. Hi, Duester. Hey, Mr. Certainly. Oh, let me pause my videos here. All right, everything looks good. Hi, Piata. Hi, Stevie. Now it's a Friday. Hello, Minnesota Mentat. Yeah, we've had lots of streams today, which has been great. Ugh. Perching on my chair here. Hey, David. Hi, Jonas. Hi, Bruce Siegel. Hopefully I'm saying that right. We'll get going just after 2 here. I like to give folks a little chance to pop in. And as always, it's pretty casual. Hi, Wagon Loads. Hi, Hams Labs. Hope you're well. I'm doing well, yeah. It's a cooler day today, which has been really nice. I have the windows open. The fan's not on. It's only 78 degrees Fahrenheit in here. I think yesterday it was like 87. It's not pleasant. 90 in New Jersey. No, thank you. I was just telling my spouse, I was like, I really, I'm kind of, I'm ready for some cooler weather. And when I said that, I didn't realize that this weekend we were going to have cooler weather. So not too sad about that. Bruce S says, just received the Morpheus 240 ESP32S2 board because I have to work on the CircuitPython port. At this point, it's more of a copy something else process. Yeah. Jonas says, I more or less randomly dropped in, but hey, CircuitPython. Hey, welcome. Yeah, we'll talk about CircuitPython. If you have questions, feel free to drop them in the chats and I'll answer them. I love doing that. Hi, Dave. Duester says it's the mid-80s here in the upstate South Carolina. Mid-80s isn't nearly as bad as 90s. G3 Holiday says 93 here. Wagon Load says it's 77 in your room. That's right about where we're at here, too. Oh, yeah, praying for rain, lots of fire in the BC interior. We did get a little. Randall says, isn't this a mukbang stream? Is that an weird autocorrect? Yep, we got a little rain. I made sure last night before I went to bed to try to close all the windows that had would let the rain in. Chicago has chance of thunderstorms and is 84. Mukbang equals eating show? Oh, cooking and eating. I mean, I just had lunch. I haven't done that yet. Yeah, thank you, folks. Letting me know what that is. Jonas says, just started to do some basic CircuitPython with my son with a bunch of Adafruit products. Awesome. I hope it's going well. We try to make it easy. Minnesota Mentat says again, much love to the timekeepers. Yeah, that's usually David DCD. I try to drop time codes in, but I'm not nearly as thorough. Yeah, we're cooking up some CircuitPython. All right, it's 2:03. I've procrastinated enough. Let me do the whole day of CircuitPython. It's been awesome. Glad you enjoyed it. I was watching the earlier streams too. I enjoyed seeing everybody's perspective on all of it. So I don't have a whole lot I was thinking of for special for CircuitPython Day, but yeah, let's get started and we can see where the stream takes us. So hello everyone, my name is Scott. I go by Tan Newt online. I work for Adafruit on CircuitPython. If you don't know what those two things are, Adafruit is an open source software and hardware company based out of New York City. I live in Seattle, so I work remotely for them and tend to do this. Just noticed. Oh, the cat's so silly. Yeah, so they do open source hardware and software. And then CircuitPython is a version of Python, which is a programming language. Really a great programming language for beginners. And it is designed to run on microcontrollers, which are these little inexpensive computers. They actually live in like lots of consumer products as well, but we take those same chips and we make them more accessible in what are called kind of dev boards, development boards. And so that's what we run CircuitPython on. And you can make all sorts of projects out of that. So those are those two things. If you want to support me, you can support me indirectly by going to adafruit.com and purchasing something there. They pay me to do these streams. They pay me to work full time on CircuitPython. So it comes back to me. If you want to chat with me and a lot of others outside of these streams, you can join our Discord server by going to the URL adafru.it/discord. Adafru.it is like Adafruit with a dot before the IT. That's our URL shortener. This is a deep dive. It happens every week, almost every week on Fridays at 2 p.m. Pacific, but occasionally it's shifted to Thursdays at 2 p.m. It typically goes for 2 hours or more, so we're about 5 minutes in. We've got just about two hours left. Questions are welcome. We've got plenty of time. It's super casual. Ask them away. I see Wagon Loads has a question here we'll get to in just a second. And yeah, so I think next week is on Friday as well. So we'll see everybody next Friday. If I do change it, we do have a deep divers role on Discord now that I will ping and let know that if it switches. And I also do have I usually do a blog post like Thursday or Wednesday, depending on when it is. So keep an eye on the Adafruit blog for that as well. I usually remember. A couple days I've done it the same day. Last up, piece of housekeeping. Let me switch to the cat cam here. Spook is the kitty kind of in the top left of the image there. He likes to move around. He's like kind of underneath. It's kind of hard to tell, but he's like underneath the door of his carrier, which is kind of funny. But he is epileptic, which means he does have seizures from time to time. It's not very common. He's been doing really well, but if I'm just like paying attention to him and not the stream, that's why. So just a heads up with that. And with that, I think that's housekeeping. Thanks again to DCD for doing timecodes. And let's answer Wagon Loads' question, even though I saw some folks in the chat answering it as well. So the first question here is, does CircuitPython run on the ESP8266 or the ESP32? Bruce replied, currently only processors with native USB, so no. But maybe if BLE workflow gets there, then yes for the ESP32. Bruce says, I did just get in some ESP32 C3 boards and another thing to stare at. And I have a collection of RISC-V boards, mostly unused. Epileptic gerbil. Interesting. Is it well controlled? Are they on medicine? So we did have ESP8266 support until including CircuitPython 3. But we found that people, the way that we were advertising CircuitPython was you plug it in, it shows up as a drive. And that's just simply not possible on the ESP8266 or the ESP32. And so what we did is at that point, we made it a decision to be very strict about the native USB requirement. So by native USB, I mean it's a specific peripheral on the system on the chips that run that can manage a lot of different types of devices, USB protocols, so to speak. So the ESP8266 and the ESP32, they have this chip that does this conversion between USB protocol and a UART, which is just like serial. But because that's how they provide USB, it means that they cannot provide mass storage, which is what makes it look like a drive. So that's why we stopped supporting ESP8266 and why we still don't support the ESP32, the regular one. As Bruce pointed out, I've been working on the BLE workflow stuff, so there's a high likelihood that as we get the BLE side of the ESP IDF, which is used kind of across all of the ESP chips, we'll be able to actually do what we've started pioneering, which is this BLE workflow. What we mean by BLE workflow is this workflow where you can transfer files over Bluetooth Low Energy, which is what BLE stands for, and you can also see the serial output. It's still really early, and it's only been implemented on only been implemented on the NRF 52840. The challenge with the BLE workflow stuff is that there's all of this host side of software. So the thing that sends a file, the thing that reads the serial output, like we have to create all of that as well, which is actually a lot of work. I didn't fully appreciate it. If you think about the way that we developed the USB side, like all of the OSs already supported mass storage because that's what a thumb drive does. Almost all of the OSs did the CDC because it's like very commonly used, which is the serial link. So with USB, it's just a matter of getting USB going and then like the OS works with it. But that's not the case for Bluetooth Low Energy, which has been a lot more work. That's been, yeah. So the device side, I think, is in a reasonable state right now, but we're not going to really be able to use it and push it until we have apps on the host side as well. I've been working on the web Bluetooth version, which will be good for Android and for Mac Chrome. We'll be able to use it. And then we're working on 2 different iOS apps. We're using, and by we, I mean folks at Adafruit. Antonio is working on Glider, which is an app that we are working to really be kind of bare bones for it. So it's Glider is just going to integrate with the iOS files stuff and just send files back and forth. And then we're also working, so Trevor is working on PyLeap, which is an app that is CircuitPython specific. So Glider is just files. It doesn't know anything about CircuitPython. PyLeap will be a much more integrated, like pull Python code from Adafruit Learn and transfer it over, and like see the serial output as well. So that's where we're at. I am not good at any of those host side things, so I'm kind of doing smaller tasks right now. Jonas asks, which devices do you expect to support? So the BLE workflow in 7.0 is currently active for all of the NRF 52840 boards, and I believe all of the NRF 52833 boards as well. We have basic support on the Microbit V2, which is the very first board that does not have USB on it. So it's the first board that has BLE only. So any of those NRF boards will do it by default. So what will happen is for boards that have USB as well, you will have to, it'll blink yellow and then it will blink faster in blue, and you have to hit reset during that time in order for it to broadcast out. I wanted to make sure that you were able to control when it was connectable. So on those boards, that's kind of what you have to do the first time. And then once it saves the information, basically once it's bonded, it will start up and broadcast so that devices who have bonded previously can connect again. If the board is BLE only, like the microbit, it will do that process without having to do the reset, because that's the only way you'd be able to use it. Wagon Loads asks, what about on OTA devices? So OTA is short for over the air. And we kind of only talked about that a bit with the ESP32S2, which typically uses over the air to reload flash firmware over Wi-Fi. So that's a little different than what we're talking about. So there's like three pieces of software you could think about on a CircuitPython board. There's the bootloader, and then the CircuitPython firmware itself, and then the files that CircuitPython runs. So that's like your file drive. OTA typically is referring to the thing, is a function of the bootloader, and that would allow you to like upgrade CircuitPython itself. We haven't really looked into that on the NRF side, so that's to be determined. We've got to figure that out still. Hi, Keith EE. Oh yeah, I should plug the... Hi, Microdev. Hi, Neradoc. And Johnny. Hello. Can the boards you're programming today access the internet? So the NRF 52840 boards cannot access the internet directly. But the ESP32S2 boards can. Yes, Microdev, I can do that. Let me cover the Reddit first. So Wagon Loads, hope that answered your question about over the internet. I wanted to plug, let me switch to the desktop. So Keith EE is also a mod for Reddit. I don't think they'd mind me saying that. But we are actively doing an AMA. So if you have questions, you're a Reddit user, you want to ask questions, here's this link. I'll put it in the chats. And kind of a bunch of us are monitoring that. I went through and did a lot earlier. So I might actually just scroll down and... I didn't want to do the AMA while I'm on my stream, because just like the hack chats, I tend not, if I answer it on the stream, I won't type it out. So I wanted to make sure and split those two up. I don't see anything new. Oh, Neradoc. That's right. Thank you for replying. Okay, so I have a stack of two. Two things we want to talk about. Keith E says a follow-up from the AMA. Microdev, I'm not doing quite your stuff quite yet because it's going to be a bigger discussion. Keith E asks, can I ask a follow-up to the question from the AMA? One user asked about threading, and the response was that it was difficult to do true threading for a number of reasons. Assuming that at some point more Pythonic-style threading gets implemented, would either CircuitPython or MicroPython run into GIL-like issues? So for those who don't know, the GIL is the global interpreter lock, and it's a Python thing. I don't know exactly where that lock happens, but I think if you look at how threading works on the RP2040 with MicroPython, we don't support it in CircuitPython, but MicroPython, you'll see that you still run into issues sharing memory. Because like even though you have two CPU cores, they're using the same memory. And so if you're ever doing an allocation or memory manipulation, you have to worry about that being a shared resource. So I think generally, yes, you'd have to worry about it. I don't know. I don't know exactly the guild details. But yeah, I don't know a lot about all that stuff. Damien's a better person to ask. Damien or Jim. Ask Patrick W says, I'm so behind, I've not listened to the Talk Python to Me episode yet, and now there's an AMA I've not seen too, so much to do. Yeah, the AMA was something that Keith was asking me about, but then like I was like, hey, actually next week's CircuitPython Day, wouldn't it be cool to have that as well? So yeah, check that out. And if folks don't know, we do actually have a CircuitPython subreddit as well, if folks are there. I tend not to, I check it sporadically, but there is one if Reddit's your jam. Okay, let's start to dive a little bit since microdev. I know it's super late for them, I think. So let's pull that up. So where do we want to start? I think I'll leave that open so I remember to check it later. So microdev has this pull request, and I want to go over the problem we were trying to debug last week because I figured it out. So remind me to cover that. So there's this PR from microdev. Microdev's been doing an awesome job helping us move a couple pieces of functionality that MicroPython put in the sys module into their own modules as CPython actually has them. So that's been really helpful. And I was looking at it, and there is a really good question. So if we look here, we can see that there's like deletions in Py stuff, and then additions into how we set up our make files. And then the way that CircuitPython is structured, for those who are new, is we have shared bindings, and this does the like shared bindings does the like translation from Python land into C land. And then you can see here that like register just calls the shared module register, unregister calls the unregister shared module. And then we have this shared module folder that actually has the logic. And I had commented it here that there's this atexit callback T global here. And I said, I think you'll want to have this in MP state so that it gets collected on garbage collection so it isn't freed. Doing it as a global risks the GC freeing the memory you need. So I think we want to talk about that, why that is. So usually in a C program, it's okay to have state. Well, it's okay. It's okay to have global state, especially if you're not going to like let anyone else touch it. But there's an extra challenge with CircuitPython in that memory is allocated. Memory is allocated by kind of the CircuitPython, MicroPython mechanics. It's a mechanic we share with MicroPython, but we have some customization to it that MicroPython hasn't taken in. So if we look at register function here, we see that there's this realloc call, and there's also this malloc call. So these are things. So what is memory allocation? So there's kind of three styles of memory allocations. There's the ones like the things at the top that you just know you're going to always have. So like this size t callback length variable is a global variable. It could be static, so it's not necessarily global, but it's kind of like it always exists. And the place in memory that variable is stored is dictated at build time by the compiler. So the compiler will say, I've got all of these variables that I know I need to allocate kind of globally up front. And that ends up in two different sections in the linker file, but there's the ones that are 0 by default, and there's the ones that aren't. And so in initialization, I think that we saw it last week as well. There's kind of two sections. There's BSS, which is all of the variables that start as 0. So instead of there's all the variables that are start as 0, and then there's all the variables that start as non-zero, and that's the data section. And so the way that the data section works is that all of those variables are kind of like squished next to each other, and then in the flash you have a copy of like all their starting values. And so one of the very first things you do when you start up is you copy all of those values out of flash into RAM in the section that you're going to store all of those pre-initialized variables. And then after that, you're going to have a section, the BSS section, which is more variables that have that global scope, but they all start as 0. So all you do is you know the range, you know how long that is, and you just set it all to 0. So it saves you flash space to split those two things apart. And then there's two other places that memory allocations can happen. There's the heap, which is the like, I don't know when I'm going to need it, but I want to have some like dynamic memory. And then there's also the stack, and the stack is all of the memory that I'm using as I call functions and store things temporarily. That's kind of what the stack does. So the stack is typically the highest end of the memory range, and it grows downwards. So what we were seeing last week is we were reading the stack pointer, which is like the low value, and reading all the way up to the top of RAM to kind of get an idea of like where in the call stack we are. But the heap is something that can be managed either by standard libraries, or it can be, in our case, it's managed. CircuitPython actually has two ways of managing more dynamic memory. One is more common than the other. We have one that is kind of supervisor level stuff, which we don't use for very much, but it allows us to store like dynamic USB descriptors. Or like small pieces of state like that, where user code may not be running, but we want to kind of hold on to something kind of longer term. And then the remaining pieces of memory between the top of BSS or the supervisor allocations all the way up to where we think the stack will be the like lowest point of the stack. So the tallest stack, all that extra range we call the heap. And the heap is just where, like, if you create a variable in CircuitPython, or you import a function or something, you can do all of that. I got distracted by the fish comment. All of that ends up in this heap, and there's a process called trying to figure out where in that space is free and where you can put new variables. That process is called allocation, which is also usually truncated or called malloc, memory allocation. And then realloc is reallocating some existing memory. So the worst case for reallocating memory is it will free the memory it has and find a new spot for it. So yeah, I think, Bruce said that one of my first streams was on memory, and in fact that is true. Before I was doing these regularly, I did do a couple deep dive streams when I was doing some tuning of the memory stuff. Sorry, let me divert. So Ask Patrick W is talking about fish and says I use OhMyZsh shell. There is also OhMyFish, which is what I use. So yeah. So Wagon Loads asks, can you defrag the heap or the stack? So the stack, the stack doesn't really have to worry about fragmentation, but the heap definitely does. And there's a lot of academic papers about the heaps, but the challenges that we have for CircuitPython and MicroPython is that they're pretty small systems. So in essence, the ability to move memory around, if you were to defrag it, you have to have some layer of indirection so that the references into that table stay the same, while as the locations in the memory change. And so basically it has a memory cost to it. So CircuitPython cannot defrag. MicroPython can't either. So this is memory allocation. And so what it does is it starts from the last place that it left off. Basically, when the last thing it tried to allocate, it kind of starts there and then looks from there until it finds a free area that's long enough for the allocation you're trying to do. The change that I made in CircuitPython, and was one of the topics of my early, like the original deep dives, was that CircuitPython, if it knows that the memory is like almost certainly going to stick around the rest of the Python script, and that tends to be anything that's in imports. So if you import and you allocate a lot of functions, like you're not going to delete those. Those are all going to be really long-lived. So CircuitPython has these mechanics to say, like, if I import something, let's just shove it. What it does is, all it does is it changes the allocation process. Instead of starting at the start of the heap, it kind of starts from the other side. And the reason to do that is that if we know it's long-lived, we can pack all the things that are long-lived together, like more densely than the stuff that we don't know the lifetime for. It's like a very crude version, kind of a manual version of what's known as a generational garbage collection process, where if you have that table of indirection and are able to move things around, you basically, from time to time, you'll recompact it. So you'll take all the stuff you allocated and that's still available, that's still in use, and move it all next to each other, and then start allocating below that again. So CircuitPython can't do that, but what we can at least do is look ahead and say, like, if it's an import, if it's a function, it's like probably going to live a long time. So we'll put it in this other section. So the other process of the other part of the garbage, or of the managing the heap, is figuring out at what point things are no longer, like, memory is no longer in use. In regular Python, this is done through a process called reference counting, which basically means that for every piece of memory that you're keeping track of how many people are using that memory. And when that number goes from 1 to 0, when no one is using memory anymore, that's when you free. In CircuitPython, because we're trying, and this is all from MicroPython. So in MicroPython, where you don't want to have extra, spend the extra data for everything that you've given out. Paul says, happy CircuitPython Day. Thanks, Paul. Instead, the way that MicroPython does it, and this is true for CircuitPython as well, is they use a mark and sweep process. So when you go to free up the memory that you can, there's a mark and sweep process. So this can happen if you import GC and call gc.collect. This will trigger this process. But otherwise, this process happens if you're trying to do an allocation. You've looked through all of memory but haven't found a spot, then it will go through this process as well, and then try to allocate it again. And if it can't allocate it after doing that collect, then it raises the memory exception, the memory exception error. So the way that MicroPython does it is that it's a two-step process. It's mark and then sweep. So you say, for all of these blocks that we think are, for all of this region that we think are in use, we're going to have a checkbox that says whether we're still using it or not. And the way that it fills in those boxes is by looking in certain places and then looking to see what that memory refers to. So, for example, imagine that you have like all of your, you have a dictionary that stores all of your variables at the top level. So what you do is you say, okay, here's all the variables that my Python code currently has. Let me look or mark all of the memory that is being referred to by those variables as in use, because they're in variables. And then what you do is you look at all of those structures, say it's a dictionary, and say and recurse. So if I'm using a dictionary, everything the dictionary uses is also in use. But then there's also there's stack memory. So there's like variables that are not globals, but they're used by function calls. G3 Holiday says, does Python have garbage collection? I have never needed it, so I don't know. Yes, it does it automatically. And this is, I should say that the reason, one of the reasons I'll push back on people about Python being bad for timing critical things is because this process can happen at any point. Which is not exactly true, but in practice, the way that Python code is written, it could happen at any point because people don't understand when the things they're doing necessarily cause allocations. And if you cause an allocation, that means that you could cause a garbage collection process, which is what we're talking about. So the question is where do we start? So for every pointer that we know we're using, we look at all of the memory it uses to make sure that we keep that as well. So it will look on the stack, so from the stack pointer all the way to the top, because there's local variables for functions that could be referred to there. It will look on most ports. It will actually look in the registers of the CPU as well, in case the references are there. It will look in the, and then it will look at the very top level stuff. So there's this MP state variable, which is kind of where we started, where microdev was asking about. And it will look in that MP state variable and collect what they call root pointers. So all of those root pointers will be collected, which means that they'll be marked as in use, and then all of the things that they point to will also be marked as in use. And so the reason that so after everything is marked, anything that was allocated but not marked as in use will then be freed, which means that in practice the values of the memory will just stay the same, but at any point the garbage collector could choose to put something else there, which would then change the value of the memory. So that's called like a use after free problem, where you're using memory after you thought you freed it. And this is why I want to do Rust at some point, because Rust has better memory sharing semantics so that the compiler can check things ahead of time. But that's not how CircuitPython works. That's not the Python world. Where you and that's good for beginners. Beginners shouldn't have to worry about memory management. They get there when they run out of memory in CircuitPython, but they shouldn't have to worry about like the details of it from the get-go. And that's why Python's great for beginners. Is so much of the Python language you don't need to know up front. You can just learn it as you need it. I think that's one of the major things about Python that's so great, is that you can start from nothing. You can learn print statements, and then you can learn the things you need to learn. You don't need to learn a lot of stuff you then need to ignore. As somebody who taught some Java, like, it's very explicit, and it makes it that you have to teach people like things that don't make sense because you can't go into those topics. Like, I remember the very first day of learning to code with Java is like learning public static void main bracket args, and like, you don't teach what public means, you don't teach what static means, you don't teach what void means. It's a lot kind of all up front, whereas Python is much smoother on ramp. You can learn things as you need them. So bringing it back to this atexit thing that microdev was asking about is that the MP state structure will be collected. And let me just see if I can't find where that happens. Oops. I have a little bit of glare. Maybe I should. I'll make it bigger and that'll help with the glare too. So basically, I think the problem is with as it's written, microdev is using a global, and that global doesn't get it doesn't get marked. Globals don't get marked unless you explicitly have them get marked. Whereas if you just put it in MP state, it will get marked, I think. So where does that happen? So main.c, I think, has a collect. Collect is the word you want to find. So here's this GC collect. I think this is a top level hook in MicroPython. So here you can see, here's how we collect the registers. So we actually get like the register values. And then there's this call of collect root. So this gets the VFS mount table. So this is like accessing the file system. We can, and then we have a bunch of hooks for different modules. So we allow different modules to hook things as well. And then here's the stack pointer hook too. Now I think that I'm pretty sure MP state is also, and it must be collected in the GC itself. So we're in Py, and then we're going to pull up GC. Let's find collect. So here's the sweep process. So sweep happens after you mark. DCD says, what if there are more than 10 registers in collect call to get registers? Then we would have a problem, and it's entirely possible we do. But yeah, could be a bug. Yeah, you hate magic numbers. That's wise. Yeah, it really should be a macro, shouldn't it? On a per port basis. Okay, so that's the sweep process. So here we go. So GC collect start, which is what we called from GC collect. And so we can see that it's doing some locking for threads. And then what it does is there's this MP state context, and it's finding the offset of dictionary locals and QString, and then collecting from there to there. And then the root pointer section is MP state VM. Permanent pointers is a thing that we added, and the PyStack as well. Root start, root end. Yeah, so I think this will cover the. I think this will cover if you just put it in MP state VM. Which I think if we look, it's MP state.h. And here's permanent pointers. Okay, so that's in state mem. MP state VM. Loaded modules. And then root pointers here. So I think you would want it in these root pointers. And then here it has this warning that the root pointer section ends here. So all this stuff won't be marked automatically. Anyway, so that's why I think there's kind of two ways to deal with this. Like, I'm going to allocate something and then I need to keep it around. You can either hook into this collect stuff that we've done, or you can add it to the MP state VM stuff. And I think we do kind of a mix of both. I kind of like being the more explicit of like, here's the things that we're going to collect all the time. Great. Microdev says, thanks for this memory dive. That really clears things up. Awesome. Well, hopefully that will get you unblocked on the exit stuff. I really appreciate you picking that up. One thing. Okay, next thing. Let's move on. Well, we have a nice bow on that. Thank you, Microdev. The other thing I wanted to talk about is last week we had this really, really weird bug, right? So last week we were struggling to use PyOCD to figure out why assertions were failing. And I was like, my mind was just blowing, and I was just like, this doesn't make any sense. Like, everything's being copied over, but it must be being corrupted and blah, blah, blah. Like all good things, I took the week off, or the weekend off, and I came back to it on Monday. I wasn't going to spend a lot of time, but I was like, you know what? Like, let me take a look at this again. And somehow I realized, you know what? I should make sure that the flash memory matches what the ELF file says. And it turns out that the UF2 bootloader for the NRF chips was broken. But it was broken in a way that if the UF2 file size was more than a megabyte, meaning you had more than 512K of code or stuff to flash, it would just stop working. Or like it would flash up to that 512K, but then fail. And so it would fail to copy that stuff. And that's usually at the top of Flash is where all of those default values for data sits. Which is just like bad news. So basically we were like partially copying NRF debug builds over. So I filed an issue on the NRF bootloader, and then TAC was quick to fix it. So if we looked at closed issues here. So I filed this issue 2 days ago, and TAC I said, oh, there's two other things. Like I wrote a script. So the script we had last week, right, compared Flash to RAM, and it was correct, but then it was still failing. And then I also realized, and this is probably part of it, that I realized that if I used PyOCD to flash the builds, it worked. Because it doesn't have this bug. So when I looked at the data section in the ELF file, I realized that the values that PyOCD was reading out for the UF2 flash version didn't match. So I posted there, and TAC replied quickly saying like, oh yeah, I can do that, or I can reproduce it, and found these issues. And there's like some reason that it's protecting some of the areas. And so it's been fixed. So if you have an NRF board and you're doing debug builds and you're using the UF2 bootloader to load them, make sure you have 061. This is a bug that's been there for a while. So that was like such a relief to figure out, because it's been plaguing me a while, I think. So that was really good to figure out. And then, the other thing. So I've been in this weird state of like, I really should do this like non-CircuitPython work for the hosts apps, but I'm like so bad at JavaScript, and I'm so like out of my league with all the mobile stuff. I was like, I can't really do that. I've got to wait for other people to find issues with the BLE side of CircuitPython and go from there. So I was trying to pick up more bugs, and I was still having this problem where GDB takes a bunch of memory. And which was the reason I was looking at PyOCD in the first place, which is just like incredibly frustrating. But Dan kind of said like, yeah, but the ARM ones that I'm working, like I don't have this problem. Like, so it must be something with your setup. You should really just use the ARM versions. And I really don't want to use the ARM versions. I like being on the cutting edge. But I was looking again at the GDB issues, and somebody said like, oh, this is not the two things I was suspecting is GDB or GCC, which is the compiler. What I hadn't thought about was LD, which is the linker. But in some of these issues, it says, oh, the linker is actually broken. It's generating this debug data that's wrong, which is causing GDB to use a ton of memory. and working correctly. So turns out they had fixed it, and I updated to binutils 27, which binutils is what includes the linker, and so that bug's been fixed as well. So it's been a good week getting past these really weird issues. Any questions? I've been talking and talking and talking. Let me just pause, since there is a lag. Ta-da emoji from Dexter. Yes. 100%. Yeah, the linker was busted. It was outputting bogus. It was outputting bogus debug data. But yeah, it's a total relief to get past that. Now I can just fix some more bugs with the tools that I've come to know and love. So I did notice. So I use Arch, and the bug had actually been fixed for a while, relatively a while, but they hadn't updated it. But the Arch folks are really responsive if you just flag it as out of date. So in fact, it's now officially updated. So this is binutils 237. I updated it yesterday manually. And then you can, if you use Arch, there's this flag package is out of date, and the packagers are generally really responsive. So thank you to Anatole for, probably said that wrong, but thank you for updating binutils for me. 2.361 has the issue, 2.37 doesn't seem to. So yeah, that's been great. I can actually debug stuff. So the thing that I was working on most recently, Ham's Lab. Nothing like when your tools have worked. I know. PyOCD is cool, but the problem, I was going to keep using PyOCD, but they don't support the SAM D21, which is where this next bug was on. So that was a bummer. Have I seen Wokwi? It's a web-based simulator with a really nice GUI showing circuits. It supports Arduino, PyPico, and they're going to release ESP32 soon. I haven't. You can connect a virtual logic analyzer. That's pretty cool, and handles PIO. Also does MicroPython, and they just started working on CircuitPython. Let's take a look. Before we get onto this next bug. Arduino projects. MicroPython project. Huh. I wonder how are they emulating this? Is this all of the G unicorn stuff? But they even have this here. I can contact with one of the devs if you're interested in. I mean, they can use me as a resource, but I don't know. I've always been kind of a downer when it comes to simulators. Like the Mako people were pretty hot on simulators, and I'm like, there's a difference between a simulator and having it in your hand. So I've always like tried to steer towards just like focusing my effort on the bunch of hardware devices in the emulator tool. Yeah, I think this is cool that somebody else is working on it, but I get so distracted already. As you all know, I get very distracted. Like, I have a Fitbit Aria on my desk here that I'm trying to hack too. So like, I have enough stuff that I get distracted by that I and this is all web stuff too, and web stuff is definitely out of my comfort zone. So yeah, I'm all for it. If they have questions on how to get it running, I'm happy to answer questions. But yeah. Keith E says, I used to be super in favor of simulators, but that was because at the time it was so expensive to even buy a dev board. Now it's a lot easier to justify grabbing one for me. Yeah, and like in terms of like where I put my time, like imagine somebody who doesn't have a computer at all. And so this is why I'm like BLE workflow is a big deal. It's like you can spend $20 on a BLE CircuitPython device, $25, and then connect it to the phone that you have. Foamy Guy points out I could see some cool opportunities for automated testing. Yeah, I think automated testing would be very... It's something we needed 2 years ago. As we start to see like some of these issues that we're hunting down for 7 are like things that used to be working and now no longer work. They're regressions. So having a test suite would prevent those regressions or reduce the likelihood. But yeah, this sounds like the person that needs to help me with that. PIO debugger. That's pretty cool. Huh. Wagon Load says, my first Arduino cost me $35. Now they're in the $5 range. I know, right? Toddbot says, hey Scott, check out this cool shiny thing. I know, I'm a sucker for shining things. And I start a lot of projects and don't finish many of them. So, yep. I think that's neat. I would point people to it. I wonder what editor this is, actually. Monico. Interesting. So the Monico editor, I think, is what VS Code uses. But yeah. Johnny says, seems my nagging about unit testing planted a seed. You nagged me long after I wanted to do on hardware and testing. But it's just a really hard problem. Like, in the first year or two of doing CircuitPython, I was doing a project called Rosie CI, which is like a Raspberry Pi with a bunch of boards hanging off of it. And I worked on it for a while and it found issues. But it's just like such a pain keeping running. Like it just wouldn't work. Simon says, how's the cats? I really must get playing with my ESP32S2 Calgon 1. Kitties are good. Oh my gosh. Can you see Spook? Let me see. Cat check. Hold on. This is worth moving the camera for. Come on. He's like cuddling with the shredder. That's hilarious. Hold on, I gotta take a picture. Oh, that's video. I don't want video. That's so funny. Keith E asks, what was the power system for Rosie? That sounds like it'd be a mess if that alone, let alone managing all the USB devices. So it was connected, the USB was connected to through a powered hub. It was connected through a powered hub, so power shouldn't have been the issue. Sorry, I'm gonna post this cat picture on Discord because it's that cute and you can't see it on the stream. That's hilarious. Ah. I can't scroll the other one. But yeah, it's hilarious. Wagon Load says, can you put a Fitbit on your cat and be notified when he has a seizure? So it crossed my mind early on when he first had them. That was like 6 years ago now. He's like 6 and he had his first one when he was 1. Basically, I was around so I could keep track of him. And he just ended up having so many that it was just kind of like he has them. He has a rough life, let me tell you. It crossed my mind. The challenge with putting anything on the cats is power supply. Right, so like, yeah, I guess a Fitbit's pretty well contained, but then you're still having to like charge it every night or every week. That gets kind of annoying. Diminishing returns, I would say. But it has crossed my mind. So the more recent thing, and the reason that I have the scale torn apart was we've been wanting to better track their weight, the cat weight, and I had this idea of putting the litter box on a scale or 2 so that every time they use the litter box, I automatically weigh them. And so that was kind of like the impetus for me to like try to get some scales to hack. So I'm figuring out how to run I got Fitbit Arias, the originals, because it's actually what we have as well. So we've been wanting to update the Wi-Fi on that. So I got 2 more from the Goodwill nearby as well. So I'm working on hacking those too. The scales. He has such a rough life. Okay, enough cat stuff. So let's see. Do I have the issue open? Yeah, it's still open. Oh, and it's still broken, so I can fix it. So the issue that I was trying to fix is, come on. Oh. We'll fix that. Would the scale auto adjust to 0 after exit? Yeah, basically what I would do is I would just weigh it perpetually and just know that like the different gaps would be. Yeah, Foamy Guy says, I don't know if the Wii balance boards and communicate things with Bluetooth. Yeah, actually that's what I was going to pick up as the Wii balance boards when I was doing all of my thrift shopping. I saw a ton of those but didn't get them because they were so big. So I went to Goodwill and they didn't have any of the balance boards. And so I was almost going to be like, But then I found the scales section and they had like 8 different electronic scales. And they had 2 of the Aria, which I already had 1 of. So I now have 3 of those. So yeah, it was just it was a trade-off between like, how many times do I have to go places to find the Wii balance boards versus just buying the 2 Fitbit Arias that already were there. And the Wii balance board is I2C then. It is, I think. But I've already found the I2C bus on the scale. On this scale. So I have 2 of them. I should be able to just put 2 under the litter box and maybe that will just work. I don't know. I do really enjoy being in electronics, being able to hack stuff like that. Scales are kind of hard to find online because they're bulky. So like you really do want to just find them in the store. So I actually got kind of lucky that 2 of the ARIAs were there. Okay, so there's this switch SAM D21 ticks to per event. And it was for this bug. Oh, I realize you can't see. So there was this bug from December of 2020. So we're a little behind. But it basically says if I do pulse in, I can't, like auto reload stops working on the Circuit Playground Express, which is the SAM D21. And here's the test code, so it was great. So I just started with this, but I put it on a Metro M0 because Metro M0s have an SWD port. Dave, who's been awesome, says I can't exactly get it in these versions. And then Robert says, oh no, it still happens. And I said 3 weeks ago, I was like, is this still in 7? And Robert was awesome enough to test it again and say like, oh, it still doesn't work. Auto reload still doesn't work. Also, remote test randomly exits after passing through the while loop, which is an error, I think. So I was picking up the SAMDs, the SAM D21, and what I found was that the SAM D21 does this weird timekeeping thing currently where there's kind of 2. So in 6, I guess, in 6 we switched to the way that the core timing of CircuitPython happens. It used to be that the Cortex series CPUs have what's called a system timer or a sys-tick timer, which is like this timer that's like right next to the CPU that tracks, that counts at CPU rates. It's great because it's high resolution, but the problem is that it's usually based on the clock that's clocking the CPU. And if you're doing sleep, then that means that the clock that you're using for timing gets stopped as well, because the sleep usually involves suspending the clock to the CPU. So in 6, we moved it, with all the sleep stuff, we moved it to all of the timekeeping to the real time, the RTC, which is either the real time counter or the real time clock. In most cases, it's a counter, meaning it's just a number. But in the STM32 case, it's a clock, meaning you get date, time, like you get hours, minutes, seconds, sub-seconds, days, that sort of stuff. And it's kind of a pain. I prefer counters, not clocks. Because like all time goes forward. You can do math later to figure out all of the clock stuff. Okay, so the SAM D21 is weird in that so we moved from the sys-tick timer to the real-time counter. There's a clock mode too, but we just use it in count mode. And there's 2 ways it's used. There's sleep, so you can tell the counter, hey, wake me up, or send an event or send an interrupt when the time is this number. So there's like a comparison that you're checking against. So that's used for sleep. And then we also occasionally have these sorts of things in CircuitPython we want to do periodically. So we have this notion of a tick, and a tick is defined. It was 1 millisecond, which is 1,000 times a second. But because a lot of real-time clocks or counters are run off 32.768 kilohertz crystals, which is 32 times 1024. That's how you get an even second, is you pick a frequency where the binary, you can divide it using binary down to a second exactly. So the tick definition with 6 changed from 1 millisecond to once 1024 per second. And then if there's more resolution than that, we have this notion of a subtick. So the problem with the SAM D21 is that the only way that the periodic ticks can be triggered was there's no interrupt from the real-time counter done on a periodic basis. There's only an event. And so the way that we were originally doing it is that we would say like, oh, if we're going to sleep, we'll just set the number. But if we're doing tick counting, we'll just, like, every time we run a tick, we'll say, okay, wake me up in another tick, which is kind of a pain to do. And then Dave Putz, who had fixed some issues with the pulse in stuff, had fixed that stuff by turning off kind of like that ticking while pulse in was happening, which made it work better, but didn't. The problem is that ticks is used by the auto reload. So when you do a write to USB, we don't immediately auto reload. We wait 700 ticks. So you do a write, we enable ticks, and we count down. So if Pulse IO is doing this stuff where it's turned ticks off, it means that the auto reload won't be able to work, which is what this bug is. So what I was switching it to do is I separated out the periodic thing because I realized late in the game that there was a way to get an interrupt on a periodic basis from the SAM D21. It's just indirect. And maybe I should pull up the datasheet. And maybe I should cover the basics of a system on a chip first. So here's the block diagram. So if you're looking at a datasheet, I highly recommend using a PDF reader that has all of the sections in it. And most datasheets will have block diagrams. So a microcontroller is much more than just a CPU. It's not like your computer where you just like plop the CPU down, and that's, I mean, they're more complicated than CPUs as well, but like generally they're just thought of as CPUs. So microcontrollers are really known as like systems on a chip. And what that means is that there's not only a processor. So if we're looking here, like this dark blue box is actually the only thing that is like actually the CPU. Like there's a whole lot of other stuff in this diagram that is not the CPU. So if we're taking a quick tour, and have I covered this? I'm not even sure. So there's the processor. So this is the SAM D21. This gray area is the high-speed bus matrix. So this is your memory bus, or at least it's the like first stage of the memory. And it has access to RAM. So there's RAM here, both the controller and the RAM itself. There's a cache and then NVM. So NVM is non-volatile memory. So this is flash. So we have RAM, flash, DMA. This is the direct memory access. And in the chart here, it actually has this M next to it. This is master, which is terminology we were trying to get away from. And then S is for slave. I'm not sure how they would, for the memory bus, what would we call it instead? It's like the initiator and the responder, something like that. The idea being that like these M's are the ones that say, hey, I need this memory, and the S's are the ones that say like, oh, that's me. Let me get that memory for you. You can see USB is up here as well. So this is USB has high-level, high-speed access. And the device service unit. So these are the things that you use for debugging. And there's an I/O bus here too. So you can do direct I/O. And then there's these bridges. So these bridges here, these three bridges, bridge B, bridge A, and bridge C, are what are known as, I think they're known as peripheral buses. That's the APB. APB is a peripheral bus, and they don't necessarily get clocked at the same speed as the CPU and the high-speed bus, but because the SAM D21's 48, I think they generally are. I generally think they are all the same clock speed. But you can actually see here that like this bridge B bus is what connects to the peripheral access controller, DMA, the NVM controller, and the USB stuff. And then there's bridge A, which has a separate access controller as well, along with the clock. Kind of this is all the clock and oscillator control. Power management, generic clock controller, more clock stuff, real-time counter. So here's the RTC, watchdog, and the external interrupt controller. So this is kind of interesting here in the one of the constraints of these memory bridges is that only one piece or one thing on this bus can be read or written at any one time. So this might, Dave tested this out, and it's possible. Good night, Dave. Thanks for hanging out. It's possible that like because we're doing something to the real-time counter, we're unable to access like the external interrupt controller. If you need to look up what Scott's going over, this is a nice guide to going along with the dive. The Advanced Microcontroller Bus Architecture. I should copy that. I'm not sure I've read it. I hope I'm right. I think this is really fascinating because so much of what people think about in terms of computer performance is centered around the CPU speed, that like people don't learn that there's other ways that your computer can be constrained. And memory accessing is one of them. And I think that's one of the reasons that like the newer Apple M1 is so much better than others, is like it does a better job at managing memory than which allows the CPU to run faster as well. But like you really need to know the performance of a system. You really need to understand the whole system, not just the CPU speed, right? Okay, let's just quickly go over this since we've done like half the diagram. There's progress. People are learning that SSDs are good. Yes, SSDs are spectacular. NVMe is awesome. I am like on board with keeping my I'm on board with keeping my computer up to date. Okay, so bridge C. So remember that like you can only read or write memory or registers, right? Registers are memory as well. You can only do that on one bus at a time. So for every clock cycle, I think it's every clock cycle, you could only do one address on it. And there's like some pipeline thing. So there's like this idea of latency that there's the value to read and then the value that you read kind of like takes a couple clocks to go to and from things. So there's a latency component in addition to how many things can be in, like how many things you're actually reading at once. Anyway, memory buses are a constraint as well. That's one of the morals of the story. So bridge C has access controller again, circoms. So circoms here are the things that do I2C, SPI, and UART. Timer counters, timer counter for control. So these are just fancy counters. The ADC, so this is the thing that's sampling stuff. The analog comparators, the DAC, that's output. Peripheral touch controller, the PTC, and the inner sound controller, I2S. So there's a couple other interesting things, and one of them's kind of like shown better than the other. One is this DMA. So there's these like tiny little gray boxes. And so what this is indicating in the block diagram is not moving memory per se, but what it's indicating is signals about the memory state of these individual peripherals. So that's what this like thin line connected to DMA is what these peripherals have. So peripherals are the name that I would use for these like different hardware blocks. So these are I think I'm sure I've said it on deep dives before, but I think of them kind of similar to an I2C device, right? Like you have a microcontroller and an I2C bus, and there's a temperature sensor on it. Like that temperature sensor is running separately of my microcontroller, but there's a way for them to communicate. So I think of these peripherals in a very similar way, except the way that they're communicating is over this APB bus instead of over like I2C. So there's a lot more wires, and they're on the same chip, but and they may be powered and clocked by the same system, but really they are independent things. Wagon Load says, can RAM and microcontrollers be accessed similar to peek and poke in C64 Basic? From C, you certainly can, and MicroPython has an API for it as well. We've talked about adding a memory API to CircuitPython, but we haven't added it yet. But there is very little memory protection in microcontrollers, so there's no reason you couldn't. Yeah. And I guess what we should also say is that like the registers are a name for memory that are kind of like the API for all of these peripherals. And they're what's known as called memory maps. So this high-speed bus matrix will decide like everything on bridge C starts with these bits, and then everything after that gets split across the things connected to it. So there's like memory. Yeah, there's a memory map we can find in here if this is interesting to folks. But yeah, so what these thin DMA lines can do is say like, hey DMA, like I just read like a UART byte. And then what the DMA can do, because it can control the high-speed bus matrix, is it say, oh, now I need to go fetch this value from bridge C at this register. And then it will write it back to RAM. And it looks like DMA has RAM access separate from the high-speed bus matrix as well. So DMA is really cool. DMA is a way to get concurrency in a microcontroller completely off of completely without the CPU's. It's all interesting, dive deep. Yeah, so DMA is really cool. It means that the CPU can say like, okay, we're gonna transfer data to this thing or from this thing based on these signals. Go do it and let me know when you're done. So DMA is really cool. It's very powerful. And it stands for direct memory access, not dogs might attack like Dexter is suggesting. But yeah, DMA is really powerful. And that's one of the reasons it's important to think about memory buses as resources. Because if the DMA is using bridge C, that means the CPU won't be able to use bridge C at the same time. So there is some sharing that happens. And especially on the SAM D21, like you could potentially really kind of bottleneck yourself across a particular memory bus. And then I guess we should also point out that these boxes on the outside, this port, so this is the port peripheral is the thing that drives the pins to the outside world. So all of the signals on the inside of the chip are like really small and really like low voltage and things. So those signals get transferred to the port peripheral, which kind of lives on the outside of the chip generally, I think. And it gets boosted up to like the signals that you would get from the outside world or vice versa. And there's ways that the port peripheral like can choose between them. The last thing, and I think the reason I brought this diagram up is this event system thing. So they don't show it at all, but they're kind of two, in the same way that there's these DMA boxes, back to this DMA thing, there really should be another thing that shows interrupts. So there are also wires that go from all these peripherals for every interrupt, and they go into the processor here. And there's a piece of the processor called the NVIC, which is the something interrupt controller. So it's taking all these wires from the peripherals, and it's able to say, these are the ones I care about, these are the ones I don't care about. If one of the ones I care about goes high or whatever, there's different ways of doing it. But signals, an interrupt occurred, then it has a process to like switch the CPU to something else. So there's interrupt lines from these peripherals that go into the NVIC and the CPU. But then there's also this event system, and this event system is not shown very well here. Controller, controllee, yeah, maybe. The other thing I like to think about in terms of, it can be like clock, like the thing that originates the clock, although on the microcontroller like this, it's not necessarily that. So the event system is a lot like interrupts, except the events go between peripherals, not to the CPU. And the event system itself has interrupt wires that go into the CPU. So popping off the stack, talking back about the RTC. So if we pull up the RTC, we can see there's a block diagram in the different modes. So it does have counter modes and a clock mode, but we're using it in counter mode. And then it has interrupts. Oh, nested vector interrupt controller. So the nested part means that interrupts can have priorities, and you can actually have multiple interrupts active at the same time. So what I wanted to find was, okay, so here's the thing on interrupts. So this says you can get interrupts. So remember, interrupts are signals sent back to the CPU saying like, hey, you should do something. There's overflow, compare, alarm. Alarm is the term if you're using clock mode, and then sync ready. So we're using this compare match in counter mode to know if you sleep, to know when to wake up. And we were previously using that for the periodic ticks as well. But if we look at events here, there's overflow, which there's an interrupt for as well. We use that. We use that because the number can run out because we're clocking it pretty fast. So we keep track of like how many times we've overflowed as well. It's basically another counter extending like the resolution. But there's also this periodic event that can be out by the RTC. And what we would really like is we would like to get the periodic thing as an interrupt. Because what we want to do is we want to get an interrupt every 1,024th of a second to call supervisor tick, which counts down until we auto reload, and a couple other things it could do. So in the SAM D21, can time trigger an interrupt? Right. So if your time is a fixed point in the future, like I'm going to sleep for 10 minutes, or I'm going to sleep for 2 minutes, like then we set the comparison register, and then that will generate an interrupt. But if we want to do this like every so often, periodically, we want a wake up thing, on the 51, the periodic register or the periodic interrupt can interrupt. But on the 21, that's not the case. However, if there's an interrupt, we can convert interrupts into interrupts. Wait, we can convert events into interrupts. So this event system, all of these wires end up from all the peripherals go into the event system peripheral. Those are known as generators. And then there's the opposite side, which is users. So users take in event signals and do stuff based on that. But we're not actually going to use that second half. If we look at here, you can see peripheral generates events, and then they get specific channels and directed to users. So how long does the interrupt take to fire and load into into state and what's the resolution of it. So how long an interrupt takes to fire is dictated by the CPU. I think that it's about, I don't know, on the order of tens of cycles. So at least the Cortex-M0, what it's got to do is it has to save all the register state, kind of like a C stack to memory, which takes time. And then it jumps to, and then it reads the interrupt table, and then it jumps to that portion of it. So the periodic one we're doing is about once a millisecond. It's like slightly faster than once a millisecond. So it's not a problem, right? Like if it's a 48 megahertz clock and we're doing it once a millisecond, which is like 1,000 times, we have 48,000 cycles per time to do it. And we don't run the tick all the time either. So yeah, it's comfortably slow. Yep. But it's super cool. Like, this is not the sort of stuff you think about if you're doing like web development. I enjoy, like, this is the machinery of the CPU that I like, as I said in the Reddit, like I really like being close to the machinery of it. Okay, so one thing they don't tell you here in this diagram is that not only can the event system kind of create these things, but it can actually do interrupts as well. So let's see, do they have another section? So there's different ways. Yeah, here we go. So there's different ways of doing it. There's edge detection, resync, async, and the async path is selected. The channel cannot generate interrupts. So it basically just passes the signal through. Mark asks, is that a CPU design naming scheme or is this the CircuitPython vernacular? Generators versus users, creating and consuming events or interrupts. I know the term generators from programming language design. So generators and users is terminology from Atmel for the SAMD event system. For events specifically. The interrupt stuff, the NVIC is something you're going to see across all like the Cortex-M stuff. And maybe since we've gone through this block diagram, maybe I'll pull up like the IMX and blow some minds because it's a lot more complicated. But maybe if folks like the block diagram, say so, and we could take a look at some other ones. This story is almost done. So the event system can generate its own interrupts. So it has overrun channel, which it basically means that multiple events came in without the user consuming them. And then there's also this event detected. So this is a way to convert an event into an interrupt, which is awesome and exactly what we want. So that's what this PR is doing. The build's still broken, so I've got to fix the build some more. But Dave did test this and said that there's still an issue with the DHT11 on it, which I'll probably have to break one out next week and figure out how to test it. Because we might actually be having like memory bus contention issues or something that's causing this. I don't know. Like writing the register can take some time. Like we have to resynchronize, but like we should be interruptible. So yeah, we haven't quite figured it out. I guess let me show you the code. So changes here. So here's like NVIC control. So there's kind of two places, and I don't know if I've covered this, but there's kind of two knobs, two places you can control interrupts. There's, does the peripheral send the interrupt out of the peripheral? And then there's also, does the CPU pay attention to the interrupt that's coming in? So the NVIC here is the CPU side of the interrupt line. And then, so we were previously doing this trick with audio DMA on the SAM D21. So that's why there's some event system stuff here. Is there's like an event signal from the DMA peripheral that we want to use as an interrupt. So we were doing that trick, and now I'm moving it out into port, and I'm removing, this is the like end start end pulse stuff that was the original fix. Because like there's this read continuous mode. Oh yeah, so that's the other piece I should talk about, I guess. So a lot of these fixes that Dave were doing is because we use, so this clock, this real-time clock, is now the source for like time monotonic. So anytime we do a call that says, hey, get me the current time, we would have to go through this process that was really, really slow. Because the clock and its circuitry is only running at like 32 kilohertz or something like that. There's this process to say, hey, I'd like to read your counter. Could you synchronize it for me? And then once you do that, it then will tell you when it's live. But the problem is that takes a long time relative to how fast the CPU is going. And so that was the original theory with why the pulse in stuff was not working. And I thought that this change would fix that, because what Dave had done in this original start pulse, end pulse thing was to set continuous mode. And the nice thing about continuous mode is that you can tell the cat wants on. What you can do is you say, hey, real-time clock, I'm going to read you a lot. Just always keep this register I can read updated. And so what I was trying to do in this PR is just like, we're going to read that a lot. Why don't we just have it always continually update? And then we don't have to do synchronization. So that's what I was doing, is just I set it continuous. But setting it continuous is a little bit of a process because you have to synchronize. You synchronize before, you set it to continuous, then you do a request, and you wait for that request as well, which is a pain. And it takes like, he said it took like 100 microseconds or something. Like, it's not fast. So here's how I turn the event on. And after I enable it, I have to set this continuous mode. And then in get count here, you can see I removed the read request synchronization stuff. So in theory, get count should actually work faster now, which actually could be like a non-trivial performance gain. We'll see. We'll see people who are like, oh, SAM D21's faster now. Anything that involves reading that clock will be faster. So I moved the interrupt after tick stuff into the same place again. I got rid of, so this is in the RTC handler is the interrupt thing that's called when the RTC. So that's the other thing about interrupts on these strips, is that it might, so I said there was two places that they're controlled. There's the peripheral side and the CPU side, but the number that can go into the CPU is limited, especially on M0s. So what some peripherals will do is they will say, I'm only going to run one wire from myself to the CPU, but I'm going to have 3 different things internally to myself that could cause it. And so what you'll see usually is that the interrupt happens, and then the first thing it does is it checks this int flag. And so this is like asking the real-time clock counter, like, oh, which thing triggered your interrupt? And then you can clear that individual thing. And this is how ticks used to work. We just say like, oh, let's set the next tick. But that's no longer the case. And now we move the event handler here. So we say if tick event is set and the interrupt is active, then we'll do tick. Otherwise, we'll do the event audio stuff. And if we're starting ticks and we haven't allocated a channel, so if it's equal to the like +1 of the valid numbers, we'll turn on the event system, we'll find a channel. We'll set it to interrupt from this peer 2 register, and then we'll disable the overflow one because we don't care. I used an NTP to set an RTC and then compared the RTC to NTP 24 hours later and found out the RTC was gaining 7 seconds a day. Yeah, that can happen. It depends on the quality of the clock source into the real-time clock or counter. Good real-time counters and stuff will actually allow you to like shift or skew the count one way or another. So you could say like every 1,000 counts, drop 1 or add 1, and that's how you can like tune it to be a little bit better. The SAM D21s, if you don't have an external clock, are terrible, really terrible. But the 32K crystals are reasonably good. So Mark says, I've seen this a few times now and I don't really understand it. The volatile keyword, that means it's going to actually check the memory location value and not start it in a register. Correct. So the compiler could say, for a non-volatile value, it can know I read the value and I'm the only one that can change it, so I don't need to like pay attention to anything else. Whereas if you're volatile, that means that the memory could change out from under you. So anytime you want to know the value, you've got to reread it, which is kind of what you're saying, yeah. Thanks, Minnesota Bentat. I will have a good weekend. I'm definitely like gonna be done in 20 minutes because I've been talking a lot. Okay, so new interrupt after ticks, which is just I moved all the code back down here. We're setting the comparison register to the next value. We're synchronizing it, and then we're setting the flags. And we have to reset continuous mode because it clears the flag in the first place, which is annoying. And then we do a check to make sure that we didn't like take so long that we should have woken up. Yeah, so are folks interested in seeing another diagram? Was that cool? Linux 203 points out temperature can affect real-time clocks, and some compensate for temperature. DCD says sure. Okay, should we do SAM D21? Yeah, Bruce S says yes. Tell the compiler that it can be changed outside the compiler's control, so don't optimize it out of existence. Okay, what do I got here? Let's do 51 first. IMX is really complicated. 51 would be a better stepping stone. Or RP2040. Let's see if they have a good diagram. Okay. So here's the diagrams do vary quite a lot. So here's the RP2040. The diagrams vary with the vendor, but what we can see here is we can see interrupts are shared, 2 processors, proc0, proc1, SIO, which is the single instruction IO stuff. So that's shared between the 2 processors, although I think the model is that you have 2 different ones. That goes out to the IOs. So this is like the equivalent of the port directory. The port directory, the port peripheral on the SAM D21. And you can see here that they've called out the fact that they're like GPIO is treated differently from QSPI, SWD, which is debugging, and the crystal stuff. So crystal signals are analog signals usually. And you can see clock generation. And then they have this bus fabric box. This is going to be the equivalent of that like high-speed bus. And DMA hangs off that along with USB. And then memory is off there, and you can see how they split the like different SRAM banks. And that's interesting because SRAM has the same constraint where you can only access particular banks of memory kind of all at the same time. ROM, so the ROM here is where the like faster math stuff is, and the UF2 bootloader will all live in this ROM. This is read-only memory. The XIP/cache, so this is memory that is used. So this is starting to get to this in the same vein of memory buses being a restricted resource. Something you learn in computer science is that the kind of further away from the CPU the memory is, like it's orders of magnitude slower. So this processor here is running at 120 megahertz or 125 megahertz, but this QSPI is 4 bits at a time running at 60 megahertz tops. So you're taking, it's just math, right? And what is the math? Like 4 bits, 60 megahertz, which means you're doing 1 byte at 30 megahertz, but you're loading 4 bytes at a time. So you're doing like 8, is it 8? Yeah, it's like just under 8 megahertz of words. So a word is like 32 bits. So if your processor is trying to run one 32-bit instruction, or if it's trying to run a 16-bit instruction, which ARM Cortex-M zeros can do, it's actually, when it can only load that at like 16 megahertz, which is outrageous. So what they do is instead is they have this cache in front, which means that if it's memory that the processor has already read once, it doesn't have to actually go out to the QSPI chip that's like somewhere here off the diagram that is like relatively slow to read. And this is why in CircuitPython we have a way to designate stuff that can end up in SRAM. So like functions we know we're going to use, we can actually spend some SRAM to put it in SRAM, and therefore this cache can have more space for stuff that is used dynamically. Okay, so that's the basics of caching. There's PIO here, 0 and 1, and then that goes out to GPIO. Oh, interesting. Wagon Load says, that is why those old mainframes were built in a circle, so the bus was as short as possible. Yeah, so like in mainframe days, the clock speeds depend on wire length. And that's still, I guess that's still true today. The longer a wire is, the slower it goes, generally. Okay, so then we kind of lastly just have this peripheral bus. So this must imply that, like, whereas the SAM D21 had multiple kind of peripheral buses, my guess is that this means that they're all on the same peripheral bus. And so this is all your SPI, UART, all that stuff is here. So that's the RP2040's diagram. It's relatively simple, similar to the SAM D21. I mean, the diagram's not quite as detailed, but like, I think they would be more similar if we looked at it in the same way. So let's go on to the 51. And generally what you'll see is they get more complicated as the kind of like the Cortex-M zeros. So Cortex-M zero is like the most basic Cortex-M, but then like M4 is going to be more complicated. And then after that, like the M7s, like the IMXs, are going to be even more complicated. Handling the RTC is kind of like a leap year adjustment. Bruce says, that's why high-speed traders put their data centers next to the stock exchange, close to the stock exchange. Speed of light. signals are still faster if they go a shorter distance. Okay, so here's the SAM D21 datasheet. And look at that diagram. That's a lot more complicated than the Cortex, or than the SAM D21. So what do we have here? We have the, starting from where we started before, we have the Cortex-M4, the MPU, and the FPU. So the MPU is the memory protection unit. FPU is the floating point unit. This does your floating point math. Systic counter is marked here. And then core site. So this is for like low-level debugging. NVM again. So this is flash again, but this time there's a cache in front of it, which SAM D21 also had? I don't remember. DMA controller is up here now. And then SRAM. And then it also has this RAM ECC block, which is if you wanted to error correct it. High-speed bus again, and the serial while, and the device service unit. And then, let's see, where do we want to start? So bridge A. So remember, these all share memory access times, and now there's orange lines for the event system, which makes that clearer. And there's a whole lot of, let's not go through all the peripherals, otherwise we'll take all day. But this looks very similar, although note that there are circoms and timers on this peripheral A. Oh, and you know one thing, yeah, there was a separate reason. So the SAM D51 was cool because you can DMA to the port peripheral, which you could not do on the SAM D21, which is kind of a neat trick. And I don't know how that's shown in this diagram. It might be in a separate place. Oh, here we go. There's this port designation here to the bridge B bus. So that means that you can, because DMA can access bridge B, you can actually DMA straight to the port, which is cool. About the 51. Okay, bridge D. Again, pretty straightforward, like a bunch of peripherals. You can see the DMA boxes are here again. So there's bridge A, bridge D, direct access to quad spy. So that's your QSPI controller. That's your flash chip. Integrity check monitor, which we don't use, but I think it's a security thing. Public key cryptography, which we don't use. Circoms again, counters again. See, they get kind of like moved different places. And then bridge C is intermixed next to this other green one. Bridge C is Ethernet, CAN. CCL is something we don't really use, but it's like glue logic stuff, almost like an FPGA, but very, very, very basic. Yeah, so there's like, what, 4 buses here? SD card controller, USB is up here off of, actually it's on one of these buses, but has direct SRAM access. Any questions about this diagram? I think it's a good place to start because it's very similar. Let me see if I have IMX already downloaded too. I'm just looking in my downloads folder. So let's do the 1010. You'll see that a lot of these memory primitives are the same because they're ARM systems. So when people license things from ARM, they get the CPU core, but they also may get the memory stuff as well. ARM does more than just the CPU. Love the Factory says, can you use DMA between Neopixels and I2C on any CircuitPython targets? So Neopixels are weird because their timing is weird. In order to use DMA, you need a peripheral that can do the weird timing. And the PIO on the RP2040 can do that weird timing. So you could probably DMA I2C to Neopixels on the RP2040. It would be weird. But you could probably do it. But generally, like the SAM D21 stuff, we actually use the CPU to do the timing for Neopixels. So you can't, like it's that there's not usually peripherals that do the timing of Neopixels directly. And then if they can, so one trick that is pretty common is that you can produce the timing for Neopixels by exploding their bits out. So you can do a SPI output, but the data coming in is like a 1 would be 1 byte of like a particular length. So you would, yeah, in order to not have to explode the data into larger, to use it as is, you need a peripheral that can do the timing right, like a PIO can. So the PIOs are really cool. I hope that we see more things like that and more microcontrollers in the future. Yeah, PIOs are really cool, for sure. Ethernet can put packets directly into SRAM there. That's nice. I guess it sends a signal when it has a full packet. Are these microcontrollers optimized for bus length between CPU and RAM, or are there other items that have a higher priority for bus speed? I think that generally everything on this high-speed bus matrix has kind of equal access. Although what we can see here is that there are some things that have access to RAM outside of that. So I guess the answer would be other things can take priority. And the SRAM controller will actually decide who gets access, who can actually prioritize it, and I think it's actually configurable as well. There is, so here's a memory mapping overview. So this is, if you ever wanted to know like what the actual address of something is, you can look at like this memory mapping overview. And then somewhere there is a chart about how they're connected. I don't know where it is. Oh, and I'm past it. Is there anything? No, pinouts. No, so there is also a chart usually in these data, at least the SAM D data sheets, that have like all the things that control the high-speed bus and all the things that can be read via the high-speed bus. And like not all of them are necessarily connected together. Which is why like the DMA on the SAM D21 could not access itself or something like that. That's like all configuration stuff. Do you want to go out? Yeah. I'm gonna kick him out. Go out. And NWK says Cypress PSOC chips have a lot of peripherals that are connected to the DMA. And the digital programmable logic array is also connected to the DMA controller. And the GPIO is connected to the programmable logic. So you could do something similar to what PIO does, is their point, I think. Okay. I like these diagrams. Let me pull up this one. I'm not... Oh, there it is, block diagram. Oh, it's not... I should pull up an STM one. So there... I remember seeing one that was... yeah, Spook's ready for the weekend. The quality of these diagrams varies a lot. And I should find the STM ones because the STM ones are good too. But there was actually one that showed the different speeds that different buses run at, which I thought was really interesting. This one is not that one I was thinking of. Yeah, so this is a lot less interesting. That's the simplified block diagram. This is the reference manual. Here's the memory map. I'm just seeing if I can. DMA mux. ARM platform. This is kind of cool. This is just the CPU block. So you can see the Cortex-M7. The ITM is an instruction trace. PPB. I don't even know what that is. DPU might be. Breakpoints. MPU is memory protection. FPU is floating point. iCache and Dcache. So these are cases where like the CPU is so fast that even like the memory buses are slower. Let's see. ROM table. TPIU is like a fancier trace debugging stuff. So it can actually spit out like everything it executes. AHB, so these are the high-speed buses. And then the AXI bus is even faster, I think. And then FlexRAM is the IMXRTs allow you to kind of decide how to use RAM banks. ITCM is instruction memory. TCM is tightly coupled memory. So you can do instruction memory. So the M7 is a Harvard von Neumann architecture. I don't remember what. There's like two classic ways CPU architectures. One is where data and instructions are loaded the same way. And then the other is that data and instructions are loaded separately. And so that's why you see here that there's a instruction tightly coupled memory, and then TCM is data tightly coupled memory. And then OC-RAM is like RAM that's generally available but is run slower. That's why the arrow kind of goes back out for AXI. Is this where this all sounds familiar, but I don't know. I don't know this datasheet as well as I do the other ones. I was hoping that maybe they have like a, you know, like a list of charts. It might have been an ST chip that I was thinking of. Do I have that in my... I don't know if I have those on this computer, but... Oh, here we go. Here's a data sheet for an L7. Let's see what this has. Or an H7. H7 is kind of the top of the line. Top of the line STM. Oh yeah, look at that. This is a cool chart. It's going to be kind of hard to read. Okay, where are we at? Let's start from the CPU like we did last time. So this is a STM32H7B0XB. And let's start from the CPU and work our way out. So here we have an ARM CPU Cortex-M7. Oh, Mark asks, I saw eFuse on there, like the thing that PlayStation 3 had to stop people from flashing their firmware backwards. Yes, I think so. I don't have a hard stop. This will be the last thing I talk about if you do, David. ITCM. So again, this is the instruction memory, two DTCMs, JTAG debugging, trace debugging again. There's an AHB here that has access to this AHB bus metrics. Yeah, Harvard Architecture versus von Neumann. I couldn't remember which one's which. MDMA, so this is like a fancier DMA. ChromArt, which is 2D DMA, so this is usually really useful for graphics. LCD TFT, this is the thing that can control like a 24-bit RGB thing on its own. WWDG, I don't know what that is. It might be Watchdog, but I could be wrong. JPEG decoder. Then there's a 64-bit AXI bus matrix. And this is only running at 280 megahertz, but I think that there are other H7s that run faster. And so you'll see like this one is fast, but then, and this bus is fast, but then like as you go outwards, that slows down. So let's follow it. So here's flash and RAM. OctoSpy. So instead of QSpy, you could actually do 8 lines. And then here's a 32-bit bus matrix. So even though this is 280 megahertz, but 64 bits at a time. Greg says window watchdog. Thank you, Greg. And hello. And then, so this 64-bit bus can talk to a 32-bit bus. So you basically get half the data, right? It's clocked the same, but it's half the data. You have 2 DMAs here. So we had two fancy DMAs at the AXI bus level, and then 2 less fancy ones here. Our USB is here, so that's what OTG is. SD card, and then there's more RAM. So it's interesting. So this AXI RAM will be faster than this AHB RAM. I'd like to use PIO for audio output rather than DMA. PIO you could do for, depends on what you mean by audio output. You could do I2S really easily. Okay, so there's a bus here, 280 megahertz to ADC stuff. And then here's, you see like a bit AHB/APB bridge. And if you probably can't read this, this says APB1 and then it says 140 megahertz. So we're down. So we had a 280 megahertz 64-bit bus. It's the fastest bus matrix. That gets then 280 megahertz, but 32 bits. And then that 32 bits at 280 then talks to this thing that is only 140 32-bit. And that's where you get all your timers, your UARTs, your SPI, kind of all this stuff that's really slow. HDMI, CSC, that stuff's all slow. And then we have another AHB, APB bridge here that is again going to 140. And this is more SPI and UART and timers again. We have, interesting here, from this AXI AHB bus, we actually have another 32 HB bus down here. DAP is like the thing that does debugging. Oh, and there's even an SPRAM. There's or SRAM. There's a 10 kilobytes of SRAM on this like slow bus here. There's a DMA mux. There's another DMA down here. More SRAM. Including the backup SRAM, so that's the one that's usually low power. So that's still at the 280 megahertz, but I think as your latency will get longer as well as you get further away. Here's your GPIO. From here, you've got power control and clock control, which doesn't need to be very fast. And then one last AHB APB bridge to another 140 megahertz bridge. And this is where you got your security stuff and your low power timer, UARTs, and voltage reference. And this is clocks down here as well. And then supply supervision. So one thing that this would be cool to have in these diagrams as well is like clock domains. So all of the, like, clocks are the thing that synchronize the signals, and to save power, you basically turn off clocks. You don't clock things because power is consumed when you change transistors. Or even just have them powered up. So typically along these memory bus boundaries, you'll have clocks and power switches as well, so that you don't have to have this part of the chip on at all, and that will save memory. So these diagrams are cool. Microcontrollers are cool. So yeah, that's oh yeah, and there's an OpenMV 87 cam. Yeah, these chips are really powerful. Very cool. All right, I am toast. Stick a fork in me. Hopefully that was a good CircuitPython Day stream. Check out the Reddit if you haven't already. If you have more questions, you can check out the Reddit today. We do have the CircuitPython subreddit if you have questions as well. But the primary place to go is to look at to join our Discord server, which you can do by going to adafru.it/discord. Hop on there. We're in the chat. CircuitPython-dev channel is kind of like, if you're getting CircuitPython building, you're adding a new board, that sort of stuff, that's the place to go. If you have questions about this low level stuff, that's a great place as well. If you want to support me, please support Adafruit by going to adafruit.com and purchasing hardware. Hopefully the thing you want is in stock, but it's been quite the trick lately. So hopefully there's things there that interest you. If you don't know what direction you want to go, I always suggest going to learn.adafruit.com and starting there. We should be... okay, so Keith says we're going to keep the AMA pinned through tomorrow. The answers there are amazing if you want something interesting to read. Yeah, and Jim from MicroPython, who we had a few weeks ago on the stream, has got really thorough answers on the AMA as well, so that's cool. Thanks to Jim for doing that. I think that's all my housekeeping. Thank you to DCD again for taking time codes, and I hope you have a good vacation. If folks want to volunteer to do it next week, please let me know and we'll figure out how to do it. And the link to the AMA, I've got it right here. Nope, and Keith beat me to it. I'll just leave this up because the cat left the room. He left me hanging, and so we won't end with the cat pet. But thank you all. Please support Adafruit. Try CircuitPython if you haven't. And have a great weekend. We'll see you next week on Friday. And on the Discord, of course.